So I'm Alex Ramirez from Google DeepMind Platforms Performance, and I'm going to try and talk a little bit about delivering performant AI solutions at our level. Since I'm terrified of running out of time, I will cover the entire presentation in just one slide, and then we can be done with it. So something that we have sort of repeated and you have seen many times is that larger machine learning models are better. Okay? So larger models require more compute performance. Not just that. I mean, I could go into details about it, but they require n-square performance with the size of the model. So there's an exponential demand for performance coming behind the AI curve. And that means we have to try and deliver more and more compute performance. And I'm going to sort of discuss a little bit that more performance means more accelerators, not just faster accelerators, but more accelerators. More accelerators, each one of them consuming more power. So there's another n-squared relationship here. More power per accelerator, more accelerators, more power. And we are under a time pressure. Okay, I mean, on the keynote for this event, we were told that we may live in a time where AGI actually happens, but we want to be the first ones to get there, so there's a race going on. So we have to deliver that compute capacity, and we have to do it fast. But something that I want to spend some time on is that it's not all about compute capacity. It's not just about having the flops, about having the systems. It's about how you use them. There's a huge number of variables involved. There's a lot of software technology. It's not that hardware eats software. It's that the software actually does a lot of the job here. So not just having compute resources, but how you use them is absolutely critical for AI solutions. We need to make forward progress in the presence of failures. The larger the system, the more failures we're going to have. We need to distribute the compute budget. I have to make a choice on the size of the model versus the number of inputs that I'm going to feed into the model while I do the training. And scaling up matters, okay? How I use the system as it is being deployed, okay? So we're done. We can go and start asking questions, or you can let me see how far I get. So larger models are better. We've seen this trend. The size of the models is increasing rapidly. And the more compute we give them, the more compute they demand. Okay, but it's not just larger is better. The mandate is to build the best model. Okay, once we have determined what is the best model that we can build, then we will make it as large as we can. So larger models, larger compute capacity, and the demand for performance is outpacing the speed at which accelerators are improving. We're getting faster GPUs, we're getting faster TPUs, we're getting more and more dedicated hardware for AI, but the demand for performance is outpacing that. So that means every new system that we deploy has more accelerators in it than the previous one. So there's another gap that's being created here. We need our software, our infrastructure to handle an increasing number of accelerators. More accelerators means more power, not just because I have more accelerators, but because the accelerators themselves are becoming more power hungry. There's no Denner scaling anymore. If we keep packing more transistors per device, the power is going to go up with the number of transistors. If I pack more accelerators into a system, the system power is going to go up dramatically. So provisioning that power is becoming an issue, and we have seen a lot of presentations about liquid cooling and about power density and how we handle all of the energy flows and so on. Okay? And there's essentially a couple of trends that we have to deal with here. Either our systems are going to get larger, or the power density is going to go up. And we actually see both things happening at the same time. So we have to deploy larger systems, more dense systems, larger systems, and we have to do it quickly because it's not just about how much performance can you deliver, but when do you make that performance available? So in the chart here, what I'm trying to represent is that if I have a choice of two systems, one of them is 1.5x better than my current system, The other one's 2x better than my current system, but it takes twice as long to deploy that system. I may be better off with the 1.5x system because it's available to me earlier. So the area under the curve, performance area under the curve, matters a lot when you're demanding compute performance. So something that's not often discussed is we need to design our systems, we need to provision our systems so that they're easy to deploy. Okay, it's not just performance per dollar, it's performance per watt, it's how much performance per day can you deliver. Okay, that is a very important metric as well that's not often discussed. So that's sort of the delivery, the provisioning side of the conversation. Something that's very important as well is what are you going to do with that system? You have a compute capacity that you can allocate to your machine learning model being developed. Well, the first thing you have to do is to keep the system operating reliably. If you have seen or if you've read the data center as a computer books that Google authors have published, what you will see is that most of our infrastructure is distributed computing, distributed software that is built for failure. But machine learning is not like that. It is a fully synchronous workload. A failure anywhere in the system stops the entire system. Larger system, more failures, we stop more frequently. That is something that literally keeps me awake at night sometimes. So the trend is unescapable. We need to design the system to be more reliable. We need to improve the time that it takes to recover from failures. We need fault-tolerant ML training algorithms. So this is not just delivering larger and faster systems. We need to think about what the software is going to do with them. Then you have to make the best possible use of your compute budget. There's trade-offs everywhere. I can build a larger system, but then I don't have much compute budget to feed it with more data. Or I can do a smaller model and feed it with a lot of data so that it learns more from the data set that I have. And this is just putting it into numbers. Okay, this is what we showed with the Chinchilla model compared to the Gopher model. So Chinchilla is a model that is 4 times smaller than Gopher, but it was trained with 4 times more data. The compute budget for training both models was roughly equivalent, and the quality of the 2 models is also roughly equivalent. But Chinchilla is a 70 billion model that is much easier to serve at scale. So this is a trade-off that we can make. We can make a big model, and then we can run out of data to train it in the compute budget that we have, or we can overtrain a smaller model. And this is where research and development still happens. And then we have to map our machine learning workload onto a scalable system. And our scalable system starts with a rack, then it becomes a cluster, and we have seen already machine learning models being trained on multiple clusters. How do you parallelize your workload onto something like that? You parallelize it on multiple dimensions, and you use all of them at the same time. So there's strong scaling. Okay, we can use our NVLink network, our ICI network to do very fast, very high bandwidth, very low latency communication and do distributed matrix multiplies and the sort. Okay, this is one way of scaling the model, but it's only going to get you as far. Okay, 16 accelerators, 200 accelerators, but we need to scale to a lot more than that. Then there's weak scaling, which is what we usually refer to as batch partitioning or data parallelism and pipelining. Okay, and that depends on how much data we're feeding to the model into each one of the training steps. So there's another trade-off. I can feed more data to get better weak scaling, but then my training efficiency is lower. I feed twice as much data into a training step, but my model doesn't learn twice as much from that data. There's a bathtub curve. There's an optimum point. Do we train at that optimum point? That's the optimum point for the learning efficiency, but it may not be the optimum point for the system performance efficiency. So if we navigate that bathtub curve, we can optimize our system for the total training time and not for the training efficiency. So trade-offs all over the place. And then we can also choose how do we balance our interconnection networks. Okay, the recent announcement for the TPU B5P essentially shows that we're building strongly connected systems with more than 8,000 accelerators. But my strong scaling doesn't go as far as 8,000 accelerators. It's limited to maybe 256. What am I doing with the rest of the strong scaling network? I'm doing a hierarchical communication. I'm doing a hierarchical reduction. First, I do the reduction inside of the strongly connected domain. And then each one of the peers in the strongly connected domain talks to its peer on another strongly connected domain. And they only have to share a tiny fraction of the data that they would have to share otherwise. So thanks to these superpods connected with ICI, I don't need a fully connected switched network on the other end. Okay, so strong scaling is one thing, but strongly connected domains can be much larger and they're still highly beneficial to your performance. So I'm going to close sort of here. What I've mentioned is that we need to deliver stronger compute capacity. And that's not just delivering more accelerators, it's what we do with them. Reduced precision is making a very important role on all of this. Provisioning is increasingly challenging. Design your systems for deployability is becoming relevant. Making the best use of the compute capacity really matters. Okay, if there's only one message, please remember this one. Keep the system running reliably. Build your system for failure, recover from failures faster, because no escaping, larger systems have more failures. Okay, make the best trade-offs. We have provided a website where you can play something with this, and scalable software. Okay, your system's going to grow over time, it's going to change platforms, and you have to be able to take your software and move it from one place to another. Okay, compulsory picture of the TPU B5P and one of our big clusters. So, questions?
Thank you so much. Questions? You can use the microphone here.
Okay.
Alex, I do have a question for you.
Okay.
So out of the curiosity, you've been talking about the large-scale models and that we need to have the best model and available. So what are your expectations? How fast can we have those large models and optimized models deployed on the market on a quite larger scale? What are your expectations?
Well, I mean, that's kind of a business decision. I mean, how much part of the compute budget is the size of the system, and then how long are you willing to invest that system onto developing a single model? Okay? We may see new models showing up once a year, twice a year. Okay, you have to gather the data, do all of the research, do all of the optimization for it, then you have to train the model, and then you have to fine-tune the model for the use cases that you're going to run with them. So, I mean, my expectation would be a cadence of once or twice a year, you'll see a new model coming up.
Wow, that's impressive. Thank you. I think we have another question.
Hey, Alex, thanks for the presentation. A question on the network scale for your strong scaling and your weak scaling networks. So you mentioned about 256 nodes in the kind of the cache coherent strong scaling network. Do you think that is going to grow materially over time, or do you think there's some fundamental limitations there?
I didn't say cache coherent.
Oh,
it is a shared memory strong scaling domain, but it's not cache coherent.
Okay.
We may see it growing, but there's a diminishing returns point. Okay, I mean, if the reduced demand that I have on the second level of the network is proportional to the size of the first one. So if I have a 16 byte reduction on the first level, then I have a 32 byte reduction on the next level, so it's kind of diminishing at some point. Okay, 8,000 chips is where we see a sweet spot right now. We may see larger domains, or we may see shrinking domains as well, for other reasons.
Great, thank you.